I hope you liked the YouTube video. We are going to look some more at the Maxwell-Boltzmann distribution. Here is the same graph as in the video. And normally we call the x-axis the kinetic energy. And for energy we normally use the letter E. And EA will be the activation energy, the sufficient energy for the reaction to happen. And that is the minimum of energy needed for the reaction to happen. Meaning that at this point, it's the minimum energy the particles can have for reacting. And anything under here, these particles will not react. None of these particles will react because they don't have sufficient energy. They don't have the activation energy. But those here in green, it's just a few particles, but they have sufficient energy and they will react. And this is quite normal. So particles will go around, bump into each other without reacting most of the time. But sometimes they have enough energy to react. We are going to look at the absolute zero. You probably have heard of it before. So that's the lowest possible temperature at the Kelvin scale. So it's 0 Kelvin, which is the same as a minus 273 degrees Celsius. And at the absolute zero, the motion of particle is minimal. And it's also no transferable heat energy. And we know that the heat energy in a system is the same as enthalpy, the delta H. Also at this temperature, ideal gas, we know that ideal gas do not actually exist. But if we assume we have an ideal gas, at constant pressure, we will reach a zero volume. It is a bit strange to think about. So I have a question for you guys. What do we think the Maxwell-Boltzmann distribution for an ideal gas at absolute zero looks like? Answer this in your... We're going to look at a catalyst. So a catalyst is something we use to speed up a reaction. And it also gives an alternative pathway with lower activation energy so that we actually can get more of the particles to react. It doesn't change the reaction, so it's still the same reaction. So if we have hydrogen gas and chlorine gas reacting, that will still end up as hydrogen and chlorine bonded together. So if we take a look at this graph we had for the activation energy. So this is the one we're having without the catalyst. We see it's the same activation energy, and on the top here, the transition state. If we have a catalyst, the activation energy will be lower. So we see that less energy is needed for having sufficient energy. So we see that I said something about an alternative pathway. So this is the normal pathway without a catalyst. With the catalyst, we have the alternative pathway with lower activation energy. So let's have a look at the Maxwell-Boltzmann distribution. So here is the green part where we do not have a catalyst. So this is the activation energy. With the catalyst, we have the activation energy at the lower kinetic energy, meaning that all of these particles, which could not react without a catalyst, can now react. So if we have a catalyst, these can react. Also, these can react. So everything about this new activation energy can react. These ones do still not have sufficient energy and no reaction will happen here. But we get a lot more of the particles which react, meaning that it takes less time for particles to bump into each other with sufficient energy. So actually what happens is that we speed up the reaction. The reaction will happen faster.